Picture this. A 1,000-ton tower crane just finished building a 60-story skyscraper. It lifted millions of pounds of steel, concrete, and glass to create one of the most impressive structures in the city. And now it's stuck. That crane that built the entire building, it can't lift itself off the roof. And getting it down is about to become one of the most complex engineering puzzles you've never thought about. When I first learned about this problem, I couldn't believe it. You spend months, sometimes years, watching these giant cranes rise alongside buildings, lifting beams that weigh more than a commercial airplane. And then one day, the building is finished, everyone celebrates, and someone asks the obvious question, how do we get that thing down? The answer is surprisingly complicated, and in many cases, removing the crane takes longer and costs more than some entire floors of the building itself. I remember standing on a construction site years ago, watching a crew prepare for crane removal, and one of the engineers told me something I've never forgotten. He said the building took 18 months to construct, but they had allocated 3 full months just for crane dismantling. 3 months. For one piece of equipment. Here's the fundamental problem that makes crane removal so challenging. A tower crane is designed to lift things, not to lift itself. The crane that built your skyscraper might stand 500 feet tall and weigh over 200 tons. To put that in perspective, that's heavier than a fully loaded Boeing 737 aircraft. Its jib, that long horizontal arm stretching across the skyline, can be 80 meters long, about the length of 3 tennis courts laid end to end. The counterweights alone, those massive concrete blocks on the back, can weigh 40 tons or more, equivalent to about 30 average cars stacked together. Every single one of these components was lifted into place by the crane itself as it grew taller, but now the crane has nothing bigger than itself to do the heavy lifting in reverse. The most common solution sounds almost absurd when you first hear it. You build another crane, but not on the ground, on the roof. Right next to the crane you're trying to remove. This smaller crane, called a derrick, gets hauled up to the rooftop piece by the original tower crane in one of its final acts of usefulness. Workers bolt this derrick securely to the building structure, usually embedding massive steel anchors into the concrete framework, and then the systematic dismantling begins. The process works in reverse order of construction, which sounds simple until you realize how many components are involved. First, the derrick removes the counterweights, those 40-ton concrete slabs that kept the crane balanced. Each slab has to be carefully rigged with steel cables, lifted just enough to clear the crane's structure, and then lowered hundreds of feet to the ground. Then the derrick dismantles the jib section by section, with each piece being carefully lowered either to the ground using extremely long cables or brought inside the building for transport down through service elevators. The counter jib comes next, followed by the slewing unit, that rotating mechanism at the top that allowed the crane to swing 360 degrees and weigh several tons on its own. Each component gets unbolted, rigged, lifted by the derrick, and lowered to waiting trucks below. But here's where the problem gets truly interesting, and this is what first blew my mind when I researched this topic. The derrick that just dismantled the main crane is now stuck on the roof. It's smaller than the tower crane, but it's still a substantial piece of equipment, often weighing 10 to 15 tons. It can't fly away, and it certainly can't lift itself down. So what happens next? You build an even smaller crane to take down the derrick. This creates what construction engineers call the Russian doll approach, a nested sequence of progressively smaller cranes, each one removing its larger predecessor until you finally reach equipment small enough to be manually dismantled and carried down through the building's service elevator. Think about that for a moment. You might have a main tower crane weighing 200 tons. That gets dismantled by a 30-ton derrick. That derrick gets dismantled by a 10-ton mini crane. That mini crane gets dismantled by a 5-ton hoist. And finally, that hoist gets taken apart by workers using hand tools, with pieces small enough to fit in a freight elevator. It's like those wooden Russian Matryoshka dolls, except each doll weighs as much as a truck and needs to be carefully unbolted several hundred feet in the air. The final crane in this sequence is usually something called a Chicago boom or a small guy derrick. These can be assembled by hand by workers on the roof, and more importantly, their individual components are small enough to fit inside a standard freight elevator. The entire process can involve 3, 4, or even 5 successive cranes, depending on the height and complexity of the building. For the Burj Khalifa in Dubai, the world's tallest building, the crane removal process was so complex that it became an engineering project studied by construction companies around the world. Now, you might be thinking there has to be a simpler way, and in some cases, there is. If the construction site has enough space and access, a massive mobile crane can be brought in from the ground to help with the dismantling. These ground-based assist cranes are engineering marvels in their own right. They can have booms extending 300 feet or more into the air, supported by outriggers that spread across an area the size of a basketball court to distribute the enormous loads. They're tall enough to reach the lower portions of the tower crane once it's been shortened through its own internal climbing mechanism. But this option isn't available for most skyscraper projects. Urban construction sites are typically surrounded by other buildings, roads, and infrastructure. There's simply no room to position a crane large enough to reach 500 feet in the air, and even if there were, the loads involved would require road closures and structural assessments of everything underneath. Tower cranes have this fascinating ability to shorten themselves using the same hydraulic climbing system they used to grow, which is something I think is absolutely ingenious in its design. Inside that boxy section near the top, there's a climbing frame with powerful hydraulic rams that can generate forces of hundreds of tons. During construction, these rams push the upper sections upward, creating a gap where workers insert new mast sections. The crane literally builds itself taller, climbing the building as the building climbs toward the sky. For dismantling, the process reverses in a way that seems almost magical when you watch it happen. The crane essentially swallows itself, removing mast sections from the top and lowering them through the climbing frame. Each section, typically about 20 feet tall and weighing several tons, gets unbolted by workers standing on narrow platforms hundreds of feet in the air. Then the crane uses its own hook to lower that section to the ground while the climbing frame ratchets down to the next level. The crane shrinks by 20 feet, and the process repeats. But this self-lowering process has important limits that determine the whole strategy. The crane can only shrink down to a certain minimum height while maintaining stability. You can't remove the bottom sections while standing on them, obviously, and you need enough tower height to support the climbing mechanism and provide structural rigidity. Once the crane reaches that critical point, usually around 100 to 150 feet, it needs external help from either a derrick on the roof or a mobile crane from the ground. The dangers involved in crane removal cannot be overstated, and this is something I think most people don't fully appreciate until something goes wrong. In April of 2019, a tower crane in Seattle collapsed during dismantling operations, killing 4 people, including 2 workers on the crane and 2 people on the street below. Investigators discovered that workers had prematurely removed more than 50 pins connecting the mast sections. These pins, each about the size of a large bolt, are what give the tower its structural integrity. They lock the mast sections together, allowing the crane to resist the twisting and bending forces that wind creates. With the pins removed, the tower was dramatically weakened, and when a wind gust of about 45 miles per hour hit, the entire structure toppled. Here's the tragic detail that haunts me about this accident. The crane had withstood much stronger winds throughout the entire construction project, winds of 60 or 70 miles per hour. But without those pins, without that structural integrity, a moderate gust became fatal. The investigation revealed that the workers had removed the pins to speed up the dismantling process, not realizing they were essentially disassembling a Jenga tower while still standing on top of it. Wind is actually one of the biggest enemies of crane removal operations, and understanding why requires a bit of physics. Tower cranes are engineered to handle specific wind loads when fully assembled. The structure is designed so that wind forces get distributed through the mast, into the foundation, and harmlessly into the ground. But during dismantling, the structure is constantly changing. Components are being removed, weight distribution shifts, and the crane's ability to resist wind forces decreases at each step. What's worse, the changes are unpredictable. One moment you have counterweights providing stability, the next moment they're gone. Industry standards typically halt all crane operations when wind speeds exceed around 35 miles per hour, and dismantling work stops at even lower thresholds, sometimes as low as 25 miles per hour. A gust that doubles wind speed can quadruple the pressure on the structure. That's basic physics of air resistance, potentially triggering catastrophic swings or tip-overs. Studies have shown that wind gusts amplified by nearby buildings account for about 23% of crane accidents worldwide. In an urban environment, buildings create wind tunnels and eddies that can be almost impossible to predict. The cost and time involved in crane removal often shocks building developers who haven't planned for it properly, and I've heard stories of projects running over budget specifically because of this final phase. Installation and dismantling together typically add between $32,000 and $82,000 to a project, but that's just the direct crane cost. You also need the assist cranes, which can run $15,000 to $60,000 per month in rental fees. You need specialized rigging crews trained in high-altitude dismantling, workers who command premium wages for one of the most dangerous jobs in construction. You need permits, road closures, and often helicopter surveys to plan the operation. And you need time, sometimes weeks or even months depending on the complexity. For the tallest buildings in the world, crane removal becomes an engineering project in its own right. The One World Trade Center in New York used a crane that stood 560 feet tall and weighed approximately 1,000 tons. Just contemplate that for a moment. 1,000 tons of steel and machinery perched on top of a building more than a quarter-mile high, and every ounce of it has to come down safely. The crane that built America's tallest building became one of the most complicated demolition projects in the city's history, requiring months of planning and execution. What makes all of this even more remarkable is that these operations happen right in the middle of busy cities. The streets below don't stop for crane dismantling. Pedestrians walk past, cars drive underneath, and life continues while workers, hundreds of feet above, carefully unbolt sections weighing several tons. The precision required is extraordinary. A single dropped bolt from that height becomes a deadly projectile, reaching speeds of over 100 miles per hour before hitting the ground. A miscalculated lift can swing loads into the building's facade, potentially causing millions of dollars in damage to the very structure they just spent years building. There's an elegant irony in all of this that I find fascinating from an engineering perspective. The tower crane represents one of humanity's greatest tools for building upward, allowing us to construct structures that would have seemed impossible just a century ago. The Empire State Building, built in 1931, was considered a marvel of engineering, partly because of the innovative crane systems used to construct it. But that same power creates a unique problem. The crane is too good at what it does. It can lift anything except the one thing it eventually needs to move, itself. The solution requires multiple cranes, careful planning, and weeks of patient work, all to remove the very machine that made the construction possible in the first place. Some modern tower cranes are designed with easier removal in mind. External climbing cranes can jack themselves down the outside of a building, reducing the complexity of rooftop dismantling. Certain self-erecting cranes can fold themselves into transportable configurations, like massive mechanical origami. Liebherr, one of the world's largest crane manufacturers, has developed specialized dismantling derricks that are specifically designed for efficient removal operations. But for the largest projects, the tallest skyscrapers, the most ambitious construction, the challenge remains fundamentally the same. What goes up must come down, and sometimes coming down is the harder part. The next time you see a tower, crane silhouetted against the skyline, consider its entire journey. It arrived at the site in pieces on flatbed trucks, sometimes requiring dozens of truckloads to transport all the components. It assembled itself section by section, growing taller as the building rose. It lifted thousands of loads, some weighing more than 20 tons, with precision measured in inches from hundreds of feet in the air. And when the job is done, when the last window is installed and the final beam is bolted, that same crane will begin its own careful descent, relying on smaller versions of itself to make the journey back to Earth. It's a remarkable cycle, one that plays out on construction sites around the world, hidden in plain sight from everyone except the engineers who have to solve this puzzle every single time. The building gets the glory, the crane does the work. And getting that crane down safely? That might just be the hardest part of the entire project.